Alright, so it looks like we're gonna have to do an integral today. Those are always fun, right? So here's the question. Find the area inside the big loop but outside the small loop of r equals 1 plus 2 sine theta. And this is a polar graph, of course, so I'll get to graphing it in a bit. I realize it needs to be split up into two integrals, but I have no ideas how to find the limits of integration for each. Please give a thorough explanation. Just getting told the answers won't help me for the upcoming tests. By the way, good on you. Should always be looking for thorough explanations to prepare yourself, because getting that answer is not going to teach you very much. You need to understand where the answer came from. If you understand the process, that will help you. Understanding just getting an answer doesn't really help you that much. So, alright, first of all, just to get a general understanding, I mean, you're definitely asking about how should the limits of integration be assigned. So let's just begin by making a basic sketch of this graph. And even if you have like a graphing calculator and you're allowed to use it or something, it's actually probably going to be beneficial for you to make a sketch of this problem, because in doing so we're going to get a better understanding of exactly how this curve is moving. Well, I'll explain as I'm doing it. So this is a polar graph, so this is why I'm making all of these different angles here. So that would be r equals 1, that could be r equals 2, r equals 3. If we really need to, we could go for an r equals 4. I'm hoping that will be enough. So let's make a table of values, and we'll just choose some likely points to plot. So I'm going to go every 90 degrees. We're going to go from 0 to 360. And by the way, let me just give you a heads up here. I'm going to be using degrees, not radians, because I already looked at some of the solution to this problem, and I gotta be honest, radians were just giving me a headache, and it doesn't really change the answer in the end whether you use degrees or radians. So as long as you make sure when you calculate your final answer that your calculator is in degree mode, right? So make sure you got that, otherwise it will definitely give you the wrong thing. But for me, it was just easier to be thinking of degrees in this case. So I'm going to go every 90 degrees. I'm going to start at 0, and then 90, 180, 270, and finding 360. And we're not going to go past 360 because everything on the graph is definitely going to loop by the time you get to 360. Because all the values of your sine function just completely start over at that point. So you're not going to be really seeing anything new after you get to 360. 0, if basically I'll show you the first one, but they're all pretty simple. R is going to equal 1 plus 2 times the sine of 0 degrees. Okay? And the sine of 0 is 0, so 2 times 0 is 0, and 1 plus 0 is just 1. So our first one is equal to 1. In the same sort of way, you probably know how to do this, so I'm not going to go too thorough into this, but if we have the sine of 90, that's equal to 1. 2 times 1 plus 1 should be 3. 180 will be 0 again, so this will actually be 1. 270, sine will be negative 1, so that's negative 2 plus 1, which means this is negative 1. And 360 goes, again, it loops around, so it goes back to the same as 0, it's 1. So I'll just start by plotting those points. This is a polar graph, so we look at our angle. This is theta 0. We've all put theta 0 degrees right there. That's 0, so at 0, r is equal to 1. So that means we're right here. I'm going to actually use a different color on that, so it will show up a bit better. There we go. That's our first point. At 90 degrees, so theta equals 90, then r equals 3. So at 90 degrees, we have 1, 2, 3. At 180 degrees, we have 1. So if you go to 180, then we go 1 unit in that direction. At 270, you get down here, and then you go minus 1 units, which means you go the opposite direction from 270. So it's over here. And then 360 goes back to 1 again. So again, like I said, it comes back to the first point. Now, what is also, well, let me start connecting the points, and we'll see that we run into a bit of a problem here. So starting from our first point, we go up here, and it's not going to look perfect, but that's okay, we don't need it to. And then we go from this down to here, and then we run into a little bit of a problem, because this is 180, and remember the next one was 270, which would be down here, but it was minus 1, so it's up here. And the question is, how exactly does it get to that point? And the thing we want to do here is actually figure out what kind of shape the graph's making between this point and this point. So one thing, and this is just sort of a general suggestion, it's often useful to determine when the graph is, when r is equal to 0. And I don't know why I shouldn't have put 2 of those, I'm thinking ahead. When does r equal 0? And we can actually solve that from our equation. So 0 equals 1 plus 2 sine theta. And we just need to solve for theta. So minus 1 equals 2 sine theta. If I go through this, then the sine of theta equals minus 1/2. And thinking about the unit circle, there's 2 locations where sine theta equals minus 1/2, right? They're basically going to be, if I had a unit circle here, it would be here and here, these 2 locations. And the reason is that, you know, sine of 30 degrees is positive 1/2. So what I'm saying is, this is 30 degrees down here, this is 30 degrees here. So, and because they're down, then they're negative. So this one will be minus 30 degrees. But I'm going to list that as 330. Because I don't want to get into negatives right now. And on the other side, this is 30 degrees past 180. So actually that will be 210 degrees. So we have 2 locations where our equation, our function, has actually an r value, a radius, whatever you want to call it, equal to 0. And so if we go back to here, we see that this point, let me use red, this point right here was 180, and then the next point was 270. 210 is between those. So somewhere between 180 and 270, we have to go through the center, because that's what we mean when r is 0, we're going through the center of the whole thing. So I mean, there's a few ways you could do it. Like, the way it actually looks is like this. So you basically, you loop down a little bit, then you go through the center, and then you go back up. And if you were to graph this and you graph a bunch of points, you see that's what it actually looks like. If you, I mean, you could also have just said, oh, well, maybe it's kind of more straight across here, which is unlikely because usually polar graphs are very loopy, they're not straight. But even if you did that, you would, since all we're trying to do is find the integral, not an exact shape of the graph, it wouldn't matter too much which option you chose here, as long as you understand that it goes from here through the center and then up. And the other side will be like the mirror reflection of that. So it will, maybe I could do that better. We'll go down here and down here. You could, of course, see this pattern if you just, it's just plotting a bunch more points. If you can't figure out what's happening, plot some more points. Like, I don't know what, say you don't know what goes on between 180 and 210. Well, then plot that and find out. The most important thing here is to understand the direction that the graph is going. Like, again, we started from, maybe I'll use a different color. We started from this point, and then we worked our way up here, then down here, then through the center, up here, back through the center, and then back to our first point. So understanding how that goes is essential when we find our integral, and also knowing exactly where it goes through the center, which is always going to be when r equals 0. Okay, so now let's go ahead and look at the integral a little bit. So, just in case you forgot, the area, it's a bit different here than you would normally have if this was just Cartesian coordinates. For a polar graph, the area is equal to 1/2 r squared d theta. And I'm not going to go through deriving that. If it's important to you, you know, I would be happy to make another video to explain it, but basically we just need to use this equation right now. And the trick here is that we have to know the limits here are alpha and beta. We have to know what those limits are very carefully. So, for instance, our graph, you know, it has like a bigger loop, which is this entire thing, and then there's a smaller loop inside of that, which is like this area, okay? And ultimately, and I think you understood this from your what you asked here, is that you're going to have to subtract the bigger one. You're going to have to subtract the smaller one from the bigger one in order to get the area in between the two curves. So our integral will have limits alpha and beta, and it will be 1/2 r squared d theta. Alright, let's think about those limits first of all. Let's look at the small loop. Now we know the small loop starts at r equals 0. So it, based on the direction this is going, it starts at 210, and then you make your way all the way around the small loop until you get to 330. And that's why it was so important for us to plot these points. We now have an idea of how this thing is actually going around through the coordinates. I mean, we understand where the small loop starts and ends, and that's probably the trickiest part of these problems. So for the small loop, let me go ahead and mark it small loop. It's going to be the integral from 210 degrees to 330. And you could just as easily use radians here, but in the end, it won't matter. So 1/2 r squared d theta. Whether big loop or small loop, our function r is going to be the same function in this case. So I'm actually going to not plug that in right now, but here are the limits for the small loop. And then the big loop. Okay, so the big loop is going to be, it starts at 330 and then it goes all the way around here until it gets back to 210. It shouldn't make a difference. If I said this was 330 to 210, that should work. Alright? I'm going, instead of calling it 330 degrees though, I'm going to call that one minus 30 degrees to 210 degrees. And the only reason I did that was just because I personally don't want to get confused. I want to be able to remember that this is going from minus 30 to 210. Like that, those values are increasing. If I went from 330 to 210, it might get mixed up in my head. Like, well, that sounds backwards, right? You should go from a small number to a big number, not from big to small. So it should technically work either way, but it's slightly harder to get mixed up if you do it this way. So that's why I switched from 330 to minus 30, okay? Alright, now, because both of my integrals are going to look exactly the same until I plug in those limits, what I'm going to do is I'm just going to work out one of them and not plug in the limits so that I can just use the answer for both and then plug in the limits and be done with it. So let's start with the big loop first, okay? I don't think I need to put that again. So again, I'm just going to ignore the limits right now. They're there, but I'm not going to worry about them yet. It's going to be 1/2 r squared d theta. So that's the integral of 1/2. R is this function 1 plus 2 times sine theta. 1 plus 2 sine theta d theta. Okay? Now, and that's really easy to do. Don't forget that this is squared, which unfortunately means the integral is going to be a lot uglier, but it is what it is. So you get 1/2. Square this thing out. It ends up being 1 plus... You're going to get 2 of these, so it's 4 sine theta. And then the most annoying one is going to be 4 sine squared theta. And unfortunately that sine squared means we're going to have to use a trig identity to replace it. Yeah. Integrals. Yeah. Alright, let's distribute the 1/2 to begin with. So you get 1/2. 1/2 times 4 is just going to be 2 sine of theta. And then this will be 2 sine squared theta d theta. Awesome. Now, let's deal with the sine squared. So, I suppose if this were a test, you would have to remember your trig identities. I'm sorry about that. But here is the trig identity we want to use. Sine squared equals 1 minus cosine of 2 theta, in our case, divided by 2. So I need to substitute that in. It's going to be 1/2 plus 2 sine theta plus 2 times, I think it was 1 minus, right? Yeah. 1 minus the cosine of 2 theta divided by 2. And that's all d theta. So the 2 here and here will just cancel out. It's about the only nice thing about this problem, I gotta say. And we can finally get something 1/2 plus 2 sine theta plus 1 minus cosine of 2 theta d theta. Alright, now let's go ahead and integrate this. Alright, so the first part is easy. Oh, by the way, the 1 and the 1/2 combine to be 3/2. So when you do that, then you just get 3/2 times theta after taking the integral, right? So sorry that these combine and you get this. I didn't think it was worth writing another step for just that. Okay, so sine. So I always have to go backwards with these. I ask myself, the derivative of a cosine is negative sine. So if I want to find this integral, I need a negative sign out front times 2 and a cosine. And then I always have to check it. So the derivative of cosine is negative sine, and then the negative and the negative would bring you back to 2 sine theta. Alright, and then going on to this part, we have, see again, derivative of sine is cosine, so this should be sine becomes, so this should be sine, so this should just be negative 1/2 sine 2 theta, and I definitely want to check that. Derivative of sine 2 theta is cosine 2 theta times 2, and the 2 will cancel out, and they'll get a minus cosine 2 theta, so that looks good. Alright, that's the end of my integral. And then I could have, by the way, I could have been writing on here the whole time limits from alpha to beta. Okay, so just continue those through the whole thing, and then at the end you'll get from alpha to beta. Now, both of these were exactly the same integral, so I just have to plug in the different limits. So let's plug in the limits for the big loop. So that will be 210. Alright, so it will be 3/2. Maybe I should write that out at least one time. So it would be 3/2 theta minus 2 cosine theta minus 1/2 sine 2 theta, and it's from minus 30 to 210. Okay. When we work that out, we get 3/2 times 210 minus 2 times the cosine of 210 minus 1/2 times the sine. 2 times 210 is going to be 420. And then I'm going to subtract 3/2 times minus 30 minus 2 times the cosine of minus 30 minus 1/2 sine, and this will be 2 times minus 30, which is minus 60. Wow. I guess I could figure these out in my head if I really thought about it, but hopefully you have a calculator available on that test, because it would be really easy to make a mistake trying to work out all these sines and cosines. So I'm going to use a calculator. Well, this... yeah, I may as well. Oops. So it's starting at the beginning. We have 3/2 times 210. That's going to be 315 minus 2 times, okay, the cosine of 210. So we'll do a cosine. Oh, and here's one thing, the only thing you have to be careful about doing it this way is to make sure that your calculator is set to degree mode, and I almost made that mistake. So the cosine of 210 is minus root 3 over 2. So it's minus root 3 over 2. And you could do approximate answers at this point as well. I'll leave it just because Well, hey, your calculator probably will not give you exact answers like mine can, so again, this is just, we're trying to find this integral. You just want the area. I'll leave it as exact. You can approximate here if you want. It's no big deal. So we'll do that, and then minus 1/2 times the sine of 420. So we're going to go with sine 420, and that's positive root 3 over 2. Okay, now we're going to subtract. That should be negative 45, right? Because that's 15 when you divide, and then 15 times 3, so, okay. Minus 2 times cosine of minus 30. Again, I know I could figure this out in my head, but I just want to be extra careful to not make a mistake. It's root 3 over 2 minus 1/2 sine of minus 60 that's negative root 3 over 2. Okay. So, let's see if there's anything that we can just directly get rid of. So this, if I look at this one, it's minus 2 and minus, so that's positive root 3. And this will be, I don't think it's going to work, so okay, 315. Those will cancel, and that will be plus root 3. Right? This one will be minus root 3 over 4. This one will be minus negative, so you get plus 45. Some of these things are in degrees. Here will be plus plus, so that's going to be positive root 3. And here, 3 negatives in a row, so that will be negative root 3 over 4. Alright, cool. So when we put these together, 315 degrees plus 45 degrees, what's that equal? 360. And then plus 2 root 3 minus root 3 over 2. And this 360 at this point would be more convenient to convert to radians, but it's actually pretty easy, right? 360 degrees in radians is 2 pi plus 2 root 3 minus root 3 over 2. So this is what I was saying. Even if you ended up with degrees in your answer, yeah, to get your final answer, you should probably calculate it using radians. But you know, it's you can easily just switch the degrees back to radians at the end. So to me, it was easier just to save myself the headache along the way. I'm going to just approximate this right now. I don't know if you want an approximate answer or not, so I'll try to do both. So it's going to be 2 pi plus 2 root 3 2 root, that's not right, root 3, and then minus root 3 over 2. Oh, yeah, I forgot my calculator tries to give me exacts. Unless I tell it not to. So it's 8.881. Now we're not done yet, sadly. But let's just keep in mind that that's there. And then we got to get the small loop. So for the small loop, it's the same exact thing, just with different limits. So it's going to be 3/2 theta minus 2 cosine theta minus 1/2 sine of 2 theta And our limits for the small loop were from 210 to 330. So 210 to 330. Okay. Go and plug it in. 3/2 times 330 minus 2 cosine of 330 minus 1/2 sine of 2 times 330 is just going to be 660 minus 3/2 of 210 minus 2 cosine of 210 and then minus 1/2 sine 2 times 210, which is 420. Alright, so 3/2 of 330, I'm not even going to go there, I'll just plug it in. 1.5 times 330, 495 in degrees, I'll be careful to mark that. Minus 2 times the cosine of 330, so we'll go cosine 330 is root 3 over 2. Minus 1/2 sine of 660 is minus root 3 over 2. Alright, then 3/2 of 210, so 1.5 times 210, 315 minus 2 times, I think I already did this. Cosine of 210 was minus root 3 over 2. I mean, I'm just, realizing that I already did this second part before, so. And that's minus 110 sine of 420 ended up being positive root 3 over 2. Alright, so 495 minus 315. I guess I'll just work that out. 495 minus 180, so 180 degrees. That's going to work. That's going to be nice. Minus root 3. This one will be plus root 3 over 4. And we already took care of that. This will be, okay, negative, 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 so a negative root 3. And this will be double negative, so it will be positive root 3 over 4. Cool. Now when we work this out, I'll convert this to radians right now. That's just pi radians. A minus 2 root 3 plus root 3 over 2. And you can approximate this. So it will be pi minus square root 3, I think. No, 2 root 3, sorry. So just 2 times root 3. Did I do the last one right? Let me just check something here. I did. Okay, cool. And then I believe it will be plus root 3 over 2. Okay. And we want an approximate answer to that, which is 0.5435. Okay. So, if you're not worried about an exact answer, at this point you just take this minus this, and you get your final answer, which, hey, I mean, I guess I might as well, let me see. I may as well work that out. The area will be 8.881 minus 0.5435. Hopefully at this point you understand why I'm doing that. It's the big loop area minus the small loop area. Gives me the area in between them, which is what we were asked to find. So 8.881 minus, I'll just do previous answer. So it's 8.3 8.33. So I'll just call it 8.34 and leave it at that. So that's one way you can give the answer as an approximate 8.34, and that's fine unless you're supposed to have an exact answer for some reason, in which case I'll just go back. It'll be 2 pi, the area would be the bigger 2 pi plus 2 root 3 minus root 3 over 4. Did I get that right? Was it really root 3 over 4? Yeah, that was right. Why? I think I might have made... Did I make... No, I combined those to get root 3 over 2. Why was this one... Oh, okay, never mind. I was good. This was root 3 over 2. I'm sorry. Yeah. Okay, and then minus pi minus 2 root 3 plus root 3 over 2. Some stuff will cancel out, you know. 2 pi minus pi is just pi. 2 root 3 plus, so negative, negative, that's plus. That's going to be 4 root 3. And then minus, minus. So this would be minus. There's 2 of those, so it would be root 3. So the final exact answer, if you need that, is pi plus 3 root 3. Let me make sure that's correct, the same as I got for my approximate. Pi plus 3 root 3. Yeah, I always make that mistake. Yeah, it doesn't give me an approximate. Yeah, 8.34. Exactly. Cool. So there's your answer, whether you want approximate or exact. And so again, my biggest tip for these problems is, particularly with polar graphs, it can be difficult to determine what direction they're going. So plot some points. You know, plot just about as many as you need to see what's happening. Don't try to plot tons and tons of them, but a few scattered, and then if you have one area, like we had this little loop down here that wasn't entirely clear, plot some extra points in that loop so you can get exactly the right picture of what's going on. Once you have that picture, then it will be much easier to determine what the limits of your integration are. Okay? That's the biggest thing with these polar area problems. I'm not sure what else I can say about this. If there's anything you would like me to clarify, please leave a comment on my channel, and I will be glad to answer that. I may, if necessary, I may even make another video to answer the point. I think that's about all I got. If you have questions about how I worked anything out here, again, just ask, and I'll be happy to clarify. Hope it helps.